Having said what we've said before, so this is what we've got. I opened up the bracket, right? Simply by what we have stated right from the beginning here. We've written the first expression, that's for this one. Remember we had the eta lambda alpha, multiplying it through, and we still have our comma k. Of course, remember we could take in the eta lambda alpha in because again is a constant. And the same thing, of course, for the second term, we can take in the eta lambda beta again because it's a constant. Differentiating it with respect to x nu will be 0. Now here at this point, you can take note that on this second term, this particular term here, I could change beta to alpha. Beta is a dummy index, so if I change it to alpha, it will look just like this first term here. I'm labeling them with the same label, 1, 1, to denote they are the same. Now if they were the same, I have a minus here between these two major terms, so the minus sign will cancel these two. So I've denoted that by that. So these two terms will be out. Again, I can pull out the eta lambda alpha just to behave anyhow, because obviously, again, because eta lambda alpha is a constant. So if I pull it out, I have these two factors left in, minus this minus that, comma xk, or x kappa. Then minus here, since this one is out, I'm left with this factor and this factor. And then again, I'm pulling out eta lambda beta, and the whole thing again is comma x nu. Now, on this whole second term, I'm changing the dummy indices here, beta to alpha, just so that it could look like this one. If I did that, this is what I will obtain on that second major term. Of course, I have two more terms here. Now, what I can do is pull out this eta lambda alpha and the 1 over 2, of course, these are all common. And then what I'm left with is all inside. At this stage, this, of course, is a linearized form of the Riemann tensor. I need not do much. But there's one other thing we can do. Of course, you can see H nu alpha is the same thing as H alpha nu. H, well, I don't think I've made any such interchange here. Kappa alpha is the same thing as alpha kappa. Now, I can decide to evaluate this metric tensor. Well, just the Minkowski metric. But this is what we're using to raise and lower. So if I were to use this to raise alpha wherever it occurred, because I don't have alpha anywhere, lambda. So if I were to use it to raise alpha, alpha is here, I raise it, and of course this is what it becomes, lambda. Minus, I raise this alpha here, it becomes a lambda. And then I raise this alpha, lambda, I raise this alpha here, lambda. And so we can have the Riemann tensor, the linearized form of the Riemann tensor in that form. That's what that will be. Of course, next we will want to obtain the Ricci scalar. What will the Ricci scalar look like, or what will it be if we were to find the linearized form of the Ricci scalar? First of all, one could just directly do that from this. I could have written the, what is it called? The Ricci scalar, remember this is the Riemann tensor. Sorry, I keep saying Ricci scalar, the Ricci tensor. This is the Ricci tensor. We've stated that this form of the Riemann tensor could be obtained from this by that, simply lowering the first index. And if we were to do that, of course, again, I can simply, by contracting the first and the third index, that is the essence of this metric tensor, I can go ahead and obtaining some conical delta here, which again changes or contracts sigma and nu, and this is what we obtain. So the Ricci tensor, not scalar, the Ricci tensor is given by that. So directly from here, I could simply say that R mu k is equal to, so I'm going to contract lambda and nu, and this is going to give me 1 over 2 of H lambda. I said lambda and nu, right? So I'm contracting lambda and nu. This is going to give me, let me use sigma, comma mu kappa minus here, H mu, sigma, here I have sigma, kappa minus H sigma, kappa, comma, mu, sigma, plus here H, kappa, mu, comma, sigma, sigma. Of course, in that way, or in that case, let me see, I can decide, for instance, to combine these two in a way that, let me see, well, one way one can decide to write this term is h mu sigma, comma sigma kappa. Remember, this is the same thing as h mu sigma on top, comma sigma kappa. Yeah, we said we can, the same metric or not necessary metric tensor, the Minkowski metrics that I used to lower this, I can use to raise this. We've done this severally before, so I don't need to. And besides, this again I can write as h sigma mu, comma sigma kappa. Again, most especially because h mu sigma is the same thing as h sigma mu. It's symmetric, so I can do that. I want to do that because I feel it will be the same with this. And again, I would like that to be the same with that. So in other words, I've been able to write this as this. One other thing I can decide to do is maybe kind of raise this mu, but I don't see any need for that. I maybe would like to leave it as such. Well, it does look like this one. So for now, I'll just leave it at that. I see no consequence or reason for which I would like to do that. Well, this particular term is interesting. Kappa mu, comma sigma sigma. Remember, in this case, okay, I've done some lowering here. In this case, what this means is I have some partial derivatives. This is the same thing as okay, so this is comma sigma, this sigma here. This expression is the same thing as saying the sigma on top, the sigma down of h kappa mu, or the same thing, of course, not necessarily equivalent, the 2h kappa mu. This is going to be the x sigma down, the x sigma on top. That's what this means. This partial derivative, the one here on top and the one below, that's just what they signify. And of course, we remember that this represents the D'Alembert. So this expression, h kappa mu, comma sigma, sigma is the same thing as the D'Alembert of h kappa mu. And then here, what else we have? Well, like I've said, we can decide to lower if we wish this term here. If we wish, we can decide to do that. But then again, I wonder why that would be necessary. One other thing I can decide to do again is raise mu here. Just make it look like that. But I think enough. This is r mu kappa 1 over 2. Here, I would like to bring this here to be the first term. This last term here, which we said is equal to this h kappa mu. And then again, let me put the negative things last. This is h sigma sigma comma mu kappa. And then here, minus h mu sigma comma sigma kappa. And here, minus h sigma kappa comma mu sigma. And that is that. Remember again, like I've said, I can decide if I want. No. I think I've rewritten this in the form that will be so that the two can look just alike. This is h sigma mu comma sigma kappa. So now this again I can box. This is the linearized form of the Ricci tensor. So we have here the linearized form of the Riemann tensor, linearized form of the Ricci tensor, and again, linearized form again, so let me use this as our paradigm here. Linearized form of the affine connector, using this expression, this is eta nu sigma, and remember is h mu nu, comma, lambda, plus here, h lambda nu, comma mu, minus h mu lambda comma nu. So again, this is one other expression that we've got. And then what else so far? We just want to make take an account of what we've done so far. Well, these were assumption of the theory or the approximations that we made right from the beginning. And we said if it were contravariant, mu nu, then it will be minus mu nu. So in this linearized theory so far, we have used these two assumptions, and we have so far arrived at the linearized form of the affine connector written in this form, linearized form of the Ricci tensor, and here we have the linearized form of the Riemann tensor. Now, hopefully, we shall move on immediately to obtaining the linearized form of the Einstein field equations, and everything else that comes with it, we just keep linearizing and see what it turns